Okay, so first of all, I want to thank the organizers for the invitation and for the great introductory talk. It definitely makes my job a lot easier. Today I wanted to talk about some of the research that I did on machine learning on large-scale graphs. And specifically, I'm going to focus on interesting trade-offs, convergence guarantees, and learning dynamics, which were results that we were able to obtain by analyzing convergence of graph machine learning models on sequences of graphs. So in order to motivate my talk, I have to start by telling you why we care about machine learning on large-scale graphs and how we do machine learning on large-scale graphs. So the reason why we care about machine learning on large-scale graphs is because the need to process information on very large graphs arises in a wide range of applications. So for instance, here on the slide, I exemplified this with a product similarity graph on the left, in which we might want to deploy a learning-based recommendation system to give better product recommendations to a user base. But perhaps more interesting for this audience, the example on the right represents a set of drones or robots that we want to control in a distributed manner. And what is interesting here is that the positions of the agents in space determine a communication graph, which essentially limits the communications or the essentially the information structure of this problem, right? And so the catch here is that we want all of the agents in this blocking problem to fly at the same speed and in the same direction, but while respecting the information structure that is given by this graph. Both of these examples are examples of problems where machine learning is the solution of choice and has been shown to obtain good solutions. And the way in which we typically do machine learning on large-scale graphs is by using graph convolutional neural networks, which are known to scale well to the large graph setting in the sense that their number of parameters doesn't depend on the graph size. Now, these GNNs, they have been able to get good performance on graphs of moderate size, meaning that we're able to train them on graphs of moderate size and get good results at that scale. But once we increase the graph size, it becomes a bit harder to train these models, and they perform a little less well. And so figuring out how to in practice scale these graph neural networks to the large scale graph setting, for instance, when you have in the order of tens of thousands of products or hundreds of agents is an important problem. So the two questions that have guided my research are the two questions here on the slide. So we have empirically observed that GNN scale, meaning that when we have a GNN that has been trained on a small graph and we transfer its weights to a large graph, we see that it does not perfect, but reasonably well. And so I wanted to understand the mathematical or theoretical reasons for why that is the case. And second, can we then use the success of GNNs on moderate sized graphs to create success at a large scale? And I'll be more clear about this point later on in the talk. And to answer both of these questions, I think it's worth turning to graph limits. And why graph limits? Well, because first of all, we're talking about large graphs, right? Like large graphs are close to graph limits, but perhaps more formally, limits reveal the intrinsic dimensionality of the data. And this is interesting because the intrinsic dimension of the data is typically smaller than the large graph size. And because, if we're able to characterize the convergence of the machine learning models on sequences of graphs to this graph limit, maybe we can learn something from this analysis that can then be exploited to facilitate the training of graph neural networks for large scale graphs. And again, I'll be more clear about this point in a few slides. So what is fortunate is that graphs indeed have limits that effectively limit their dimensionality. There are many models that people have assumed. Here I focus on Graphons. And here on the slide, I'm just exemplifying how even, in the real world setting, even when we're far away from these models, we do see that as we increase the number of nodes here in the case of the product similarity network, the number of products, we do see that there's some overall convergence of the global and local graph structures. And graphons and sequences of graphs converging to graphons, the notion of convergence there, even though I'm not going to go into the detail, really captures this sort of local global convergence. But what's the difficulty here, right? The difficulty is that even though, there is a theory for convergent sequences of graphs converging to graphons, graphs are irregular, right? They don't have a regular structure. So they don't have the Euclidean structure that, for instance, time and image signals have in the limit. And so convergence of filters or more general systems like graph neural networks on top of these sequences of graphs is not a given, right? So it's a result that still needs to be established. Now, as a disclaimer, what I will do in this talk is I will flash essentially the convergence results that we derived for graph neural networks, or more precisely graph convolutions, which are the main building blocks of graph neural networks. But I am not going to go into the details of the actual convergence results. I will rather focus on interesting facts that we discovered from this convergence analysis and extensions that allowed us to devise better learning algorithms for graph neural networks and to analyze the learning dynamics of graph neural networks. And I'm happy to discuss the actual convergence results offline. But before I do that, let me talk a little bit about graph convolutions and GNNs. So here, assuming the setup that was discussed in the previous talk, where we have a graph that is represented by the adjacency matrix, which here I write S, and a graph signal X, a graph convolution is simply a linear shift invariant filter on top of this graph signal X. And the way in which we represent this mathematically is as a polynomial in the adjacency matrix of the graph applied to the graph signal X. And we can interpret each term of this polynomial as a shift or a diffusion of the data on top of the graph, as you can see in this diagram. And a graph neural network is a very simple essentially architectural modification of a graph convolution. A graph neural network consists of a sequence of layers, each of which consists of a graph convolution, here represented by the blue blocks, followed by a pointwise nonlinearity, which is node-wise in the case of the graph, such as the ReLU, the sigmoid, any nonlinearity that you use in a conventional fully connected neural network. Here, the only difference is that the nonlinearity applies pointwise to each node. But other than that, this is basically just a sequence of graph convolutions. Now, moving on to the graph limit side of things, right? So moving on to the graphons themselves, what is a graphon? So a graphon, the technical definition is that the graphon W is a bounded symmetric measurable function mapping points from the unit square to the unit interval. So it's basically a symmetric kernel on the unit square that is bounded. But the way in which we think of graphons here, or that is easiest to interpret, is as a weighted symmetric graph with an uncountable number of nodes, where the nodes are the points of the unit interval and the edge weights or the edges are the graphon values evaluated at the points, at the labels UN. So this object can be interpreted both as the limit of a sequence of graphs, in the sense that the densities of certain motives in these graphs converge. And alternatively, it can also be seen as a generative model of graph families that can be generated by sampling edges UIUJ, Bernoulli with probability WUIUJ. And so because of these two interpretations, we can think of a graphon as identifying a family of similar graphs. And here on the slide, I just have as a simple example, a sequence of stochastic block model graphs on two communities converging to a stochastic block model graphon. If you look at this slide from left to right, but alternatively, you could also look at the slide from right to left, and you could imagine how you can use this graphon on the right to sample any one of the graphs on the left by first sampling points from the axis, right, from the x-axis, and then evaluating the edges on the square. Now, in the same way that we defined graph convolutions, we need to define Graphon convolutions, right? Because what we want to do is to characterize the convergence of graph convolutions to Graphon convolutions to be able to establish the convergence of graph neural networks to Graphon neural networks. So how do we define a Graphon convolution? Also, the first thing that we have to do is define the analog of the adjacency matrix, right? So in the case of the Graphon, the analog of the adjacency matrix is this operator TW, which is essentially just the integral linear operator with kernel given by the Graphon W itself. And each application of this operator to now the Graphon signal capital X corresponds to a diffusion of information in the Graphon. And so the Graphon convolution is a polynomial of this operator applied to the Graphon signal. And it's easy to see that this has essentially the same algebraic structure as the graph convolution. Now, in the same way, we can define a Graphon neural network, which is, again, just a composition of Graphon convolution, with pointwise nonlinearities, and then each one of these compositions forms a layer, and we stack layers to form a Graphon neural network. And so, again, a Graphon neural network, it is not difficult to see that it has the same algebraic structure as graph neural network. The only thing that changes is that one operates on the graph, the other operates on the graph. So now that I have introduced these preliminary definitions, let me talk about the convergence analysis of these graph neural networks and what we have found out when we went and looked at their convergence. So first of all, convergence of graph neural networks, in order to establish that result, what we really need to look at is the convergence of the graph convolution, right? Because the pointwise nonlinearity is node-wise on the graph, and similarly node-wise on the Graphon. So the convergence of that part is easy to show. But the graph convolution is the one that is a bit more complicated, right? So, you know, even though this result is not trivial, it is also not unexpected that graph convolutions converge to Graphon convolutions, provided that their spectral response, which I have not defined here, but again, I'm happy to discuss this in more detail offline. But the spectral response, you can think, is essentially the effect of the graph convolution on the eigenvalue spectrum of the graph. So if this function is continuous, then we can show convergence of these graph convolutions. And the reason why I say this result is not unexpected is because, you know, under the Graphon theory of convergence, that theory essentially defines a metric for graphs, right? That allows us to compare graphs as similar or different, and to show convergence of graphs under this metric. And once you have an operator that is continuous under a certain metric, it is not unexpected, or it's not counterintuitive to expect that this operator would converge on top of the sequence, right? So this is why I didn't want to focus on convergence itself, but I did want to focus on the condition here that we have for this theorem, which is that the spectral response h of lambda of the graph convolution not only has to be continuous, it has to be Lipschitz continuous with bounded Lipschitz constant. And let me skip one slide and then I'll come back. And the reason why this restriction or assumption shows up is because the convergence result is actually a spectral result, in the sense that it relies on the convergence of spectra of graphs to the spectra of graphons. And this is good because, you know, provided that the graph and the Graphon convolution have the same coefficients and therefore the same spectral response, convergence of spectra means that graph convolutions converge to Graphon convolutions. But it's also bad because since graphons are compact operators, the Graphon operator is a compact operator, what happens is that its spectrum accumulates near zero. And due to this accumulation of spectrum, it can be hard to match graph and graphon eigenvalues close to lambda equal to 0. And so in order to have convergence and a good rate of convergence, we need our filters to be almost flat in this region of the spectrum, which is what imposes this Lipschitz continuity assumption that we need on our filters in order to have convergence. And so the reason why I wanted to bring this up is that this is a non-trivial observation, right? In order to have convergence, in order to have filters in neural networks that are convergent, we need them to be such that they're not very discriminative for eigenvalues, or if you want to call them graph frequencies, close to 0, which, as it turns out, they are associated with high graph frequencies or high oscillation modes on graphs. Now, I just quickly want to come back to this slide where here what I'm showing is essentially just the non-asymptotic version of that convergence result. And I also call this a transferability result. And transferability is something that is more useful in practice because what essentially this transferability result is doing is it's upper bounding the error that you make when you transfer the same graph neural network with the same coefficients across two graphs associated with the same graphon or from one graph to a graphon. And it is showing that this error decreases with the size of both graphs, and is showing the explicit dependence of the bound on the Lipschitz constant AH of the filters of the GNN, which allows us then, you know, given this upper bound, to design graph neural networks in the sense that we can train them on small graphs whose size is determined by this bound, right, by evaluating this bound, and then transfer them to large graphs with performance guarantees given by this bound, right? So that's another interesting consequence of convergence, transferability in the sense that we can train on small graphs and transfer to large graphs. So let me skip this numerical example so I can get to the next part of my talk, where I want to talk about an extension of transferability, which is learning by transference. So what is the difference between transferability and learning by transference? So in transferability, we're training a graph neural network on a small graph, which is, you know, a single graph, and transferring to a large graph and making an error, and we can't really escape that error, right? But can we do better? And the answer is yes, we can do better by, instead of training the GNN on a single small graph, training it on a sequence of graphs, of increasing graphs, converging to the limit graph or to the limit graphon. This is what I'm showing here on this algorithm. And what we were able to show by training graph neural networks now on sequences of graphs as opposed to a single small graph is that this algorithm has convergence guarantees, in the sense that provided that the difference between the gradients of the loss on the graph, on the finite size graph, and on the limit graphon is smaller than the norm of the gradient on the limit graphon, this algorithm converges to the solution of the optimization problem on the limit graphon in a finite number of steps. So the way in which I interpret this result is to mean that we're essentially leveraging convergence of the graph sequence in the convergence of gradient descent when doing optimization on these graphs. And here, I just wanted to show a numerical example, exemplifying how this learning by transference algorithm works well in practice, by showing how it's when we compare it with training a graph neural network directly on the large graph, we are able to save in terms of computational complexity. So if you look at this, the figure on the center of the slide, the red curve, which is flat, shows the control cost achieved in that flocking problem when we train the controller directly on the 100 agent graph. So we want the cost to be small. And the orange, green, and blue curves are showing the control cost achieved at each epoch by our learning by transference algorithm. And at each epoch, we're essentially increasing the number of agents. Depending on the color of the curve, we have different rates of increase, right? So 2 for the blue, 5 for the orange, 10 for the green. And what we can see is that with as little as 20 to 45 agents more, yeah, with as little as increases to up to 20 or 45 agents, we get a control cost that is comparable to the control cost achieved on the 100 agent network. And we save a lot of complexity, right? And we also save a lot of time, which we can see when we look at the plot on the right, which essentially shows the time per epoch depending on the number of nodes of the graph. And again, this knowing that we have convergence guarantees as well. So I'm going to skip this other example so that I can conclude by talking about the second extension that we obtained from this work by analyzing convergence of graph sequences to graphons, which is the Graphon neural tangent kernel. So to give you a bit of background, the neural tangent kernel is a kernel that arises when we look at the gradient descent dynamics of least squares regression using neural networks. And when we look at the time derivative of our neural network outputs, we see that this kernel in red arises, and that if we take the width of the neural network to the infinite width limit, this kernel theta converges to an operator that remains unchanged during training. So what this means in practice is that in the infinite width limit, the gradient descent dynamics of training the neural network is deterministic. And so that we can analyze what happens in this limit by just doing kernel ridge regression with this kernel, which is called the neural tangent kernel. And the reason why this is interesting, even though it's a model and even though it's assuming that we are in the infinite width limit, is because the principal eigendirections of this neural tangent kernel correspond to the directions of fastest learning of the neural network. And so they tell us a lot about the learning dynamics of these neural networks. Now, because graph and Graphon neural networks can be seen as neural networks with an additional channel dimension for the graph, right, or for the nodes, it is easy to extend the neural tangent kernel to graphs and to Graphons. So people have extended the NTK to the graph to define GNTKs. And in this work, we also extended it to the Graphon NTK. And similarly to how GNNs and Graphon NNs were the same algebraic object, we observed that the GNTK and the Graphon NTK are also the same algebraic object. And so, not surprisingly, it is possible to prove convergence of the graph neurotangent kernel to the Graphon neurotangent kernel. So this is what this theorem is saying. And the two important consequences of these results are first that, you could, similarly to how you can train a GNN on a small graph and transfer to a large graph, you could fit the GNTK on a smaller graph and transfer the kernel regression weights to make predictions on the large graph. But more importantly, the GNTK fitted on a small graph, provided that it's large enough, can be used to infer the training dynamics of GNNs on large scale graphs. So to exemplify how this can be used in practice, in this experiment, we simulated an opinion dynamics process in a stochastic block model graph, where the goal was essentially from, looking at the process at time t equal to 0, I want to predict what it looks like at time t equal to 10. And you can imagine this as being a consensus process. And what we did is we trained a graph neural network and we fitted a graph neurotangent kernel to this problem. And we projected on the y-axis, and on the y-axis, we plotted the projection of the output of either the GNTK or the neural network onto the second adjacency eigenvector. And on the x-axis, we projected the input onto the second adjacency eigenvector, and second here because it reveals the community structure. And what we see from left to right is that as we increase the width of the graph neural network, the variance of these curves across initializations decreases. So kind of corroborating the observation that, in the infinite width limit, the NTK dynamics are, the GNN dynamics are deterministic and determined by the NTK. And also the GNN and the GNTK curves align, again, corroborating this observation. And so this exemplifies, is essentially an empirical manifestation of those numerical results. And finally, this is my last slide. Here in this example, we just trained the graph neural network and fitted a GNTK to citation networks, where the goal is given some features corresponding to papers, which are the nodes of a graph, classifying these papers into different scientific communities. What we did then was that we trained a GNN and fitted a GNTK to solve this problem. And then we plotted on the right the dominant eigenvalue of the graph neurotangent kernel for different graph sizes. And what we saw is that this eigenvalue converges as we increase the graph size, indicating that so we haven't looked at convergence of eigenvectors, right? But this should imply that the eigendirections of the GNTK are converging as we increase the graph size. That's corroborating that we could look at GNTKs fitted on smaller graphs to infer the learning dynamics of graph neural networks on larger graphs. So since I am a little over time, I'm going to skip my conclusions and I'm happy to answer any questions. And again, thank you for the invitation.
Can you hear me?
Yes.
Okay, thank you so much, Luana. So I think we have time for maybe 2 questions. Any question here or on Zoom? I'm monitoring the Zoom here. Yep. We have to go behind the microphones. Yeah.
Hi, Luana, can you hear me?
Yes.
Okay, yeah, thanks for the very nice talk. So I had a quick question about the design of Graphon models then. So, this is a robotics conference, and so a lot of the stuff that, we're really concerned about is physically embodied systems. And so a lot of the interactions that we care about are interactions that pertain to something involving spatial locality. So have you looked at Graphon models that, or do you have any sort of thoughts on particular Graphon models that are especially suited to describing that kind of a motif, like spatial locality and things of that sort that would be especially relevant for this audience? And do you have any thoughts on designing machine learning mechanisms that are especially designed for that kind of interaction structure? It seemed like that might have been relevant to some of the flocking examples you gave, perhaps.
Right. So yeah, that's a very great question. So something that I didn't mention is that maybe these random geometric graphs that we have, for instance, in the flocking example, aren't the best example of the dense graphs that are better modeled by Graphons. So in the product recommendation example, yes, that can be modeled as a Graphon. The random geometric graph of agents, not so much. So I think there are two ways that I can answer this question. One is, perhaps a better model for random geometric graphs is, say, a manifold of the d-dimensional space on which you have your agents, right? Or, and this is the more general definition of a graphon, you could imagine that here, instead of having a kernel that maps points of the unit square into the unit interval, you could have a model that composes two functions, essentially. One that maps points from some d-dimensional space to the unit interval, and then a kernel that maps essentially the unit square to the unit interval, right? So you can decouple these two things, and this would allow you to represent more general graphs, such as, for instance, the multi-agent system graph, right? I have done some work on graph neural networks for graphs sampled from sparser graph models, such as manifolds. And there we observe very much the same type of convergence result. Obviously, there's a few differences because there are particularities to manifolds that are a bit different than what we have in the case of graphons, but we do observe convergence and transferability and a lot of the same trade-offs that we observed here.
Okay, thank you.
So we have another question.
Thank you for the great talk. I'm Hyosang from Cranfield University. Just one question. This method allows the analysis on trade-off between transferability and convergence. Is there any way you can, maybe this is not really the right question, maybe adjust or tune the trade-off between the transferability and convergence? Because if I want to control this trade-off, is there any way you can do something?
Absolutely. So that's also a very good question. So what we do in practice is that if we want to improve the transferability of our models, what we can do is we can penalize the Lipschitz constants of the graph convolutions, right? So in this way, we can get a graph neural network model where the graph convolutions have low Lipschitz constant, and we can expect from the theory that those models would be more transferable, right? So, for instance, in this slide here, I didn't describe this example, but this is the recommendation system example where we're training on a smaller product network and transferring to the larger one. And what we're plotting on the right here is the difference between the loss that we get when we train on the small graph with size given by the x-axis, and on the large graph, which has 4,000 products. And what we see is that the transferability error of the Lipschitz GNN here, which is this GNN trained by penalizing the Lipschitz constant, is lower than the transferability error of a GNN in orange that was trained without any additional penalty term. So you can definitely add penalties to control this trade-off in practice.
Yeah. Maybe we have time for a very quick question. Yeah. Yeah. Thank you.
Thank you very much for the talk. I'm really curious about the scalability aspect for multi-robot control. So from my experience, it seems like GNNs can scale when there's when the task is kind of simple maybe, and the behavior of most robots is kind of similar, while they might fail in more tight environments, in more complex tasks. So do you have a comment on that? Is it something that you would verify?
Yes, yes, I agree with you. And in particular, I know that so I don't have much of a robotics background, but I have colleagues that have worked on GNNs for robotics, and what they have noticed is that in a lot of these problems, first of all, you have to take the time dimension into account, right? Because things are constantly changing. These are dynamical systems, right? So it might be better to use models such as graph recurrent neural networks. And in addition to that, people have obtained better results in more complicated problems by considering heterogeneous graphs where you allow nodes to represent heterogeneous agents, right?
Oh, I see.
I don't have experience with that, but I know that you do need more complicated models for more complicated problems.
Thank you very much.
You're welcome.
So let's thank Luana, please.
Thank you.
Thank you very much, Luana.